Last class, we discussed this result that says that a Mobius transformation preserves the family of circles in the Riemann sphere or extended complex plane C hat. Here, the goal is to show that any Mobius transformation will map a circle in the extended complex plane to another circle in the extended complex plane, which means that lines or circles in the complex plane get mapped to lines or circles in the complex plane. So we are going to prove this now. Before we can go into any detail with the proof, let's explore exactly what do we mean by the equation of a circle. Normally, we are used to see the equation of a circle or a line written in real coordinates, but let's write it in a more comfortable way to deal with complex analysis. Typically, they look like this: alpha z bar plus beta z plus beta bar z bar plus gamma equal 0. And here, alpha, gamma are real numbers. Okay. We have that beta is a complex number, and then we have a compatibility condition that says alpha gamma less than the modulus of beta square. Okay, so this is the general form of the equation of a circle in the Riemann sphere. Quick check. So if you notice, this is the magnitude of z squared, so this is a real number. And here we have two numbers that are conjugates. So this we identify as the real part of a number. So we have real, real, therefore alpha and gamma need to be real for this equation to make sense. Okay, let's explore more that idea. Why is this the equation of a circle? So if you notice by what I said, we actually have here alpha modulus of z squared, and then here we have twice the real part of beta z. Okay, and then we have gamma. But then here, when we write, let's say beta equals a minus ib. This minus is just for convenience. So z equals x plus iy. Then beta z is going to be, you see, alpha x, ax, and then the other real term is going to be this one. It's going to be by times minus I squared, which is plus 1. So this is plus by. Okay, and we can continue, but this is plus I, and then more terms. Okay, that doesn't matter. This is the real part we are looking at. So then we have alpha x squared plus y squared plus 2ax plus 2by plus gamma equals 0. And this is a much more reasonable equation for a circle, okay? Here, notice if alpha equals 0, we get the equation of a line, clearly. Okay, so here, if alpha is 0, this describes a line. Okay. And if alpha is different from 0, then what happens if alpha is different from 0? Let's identify more clearly the circle we are dealing with. So this is alpha x squared plus 2ax. Let me leave some space here. We are going to complete the squares. Alpha y squared plus 2by, right? And then we have plus gamma equals 0. I'm leaving some space because we are going to complete the squares, right? Now, if we want to complete the squares, here we clearly have the square root square, right? But we don't see it here. So here we need alpha square, sorry, a square over alpha. Okay, so that we have in the first term square root of alpha x plus a over square root of alpha, all of it squared. Quick check. Square root of alpha x squared plus 2 square root of alpha x a square root of alpha. These two cancel out. Okay, plus a squared over alpha. Everything good. Okay, here similarly, here we have plus b squared over square root of alpha. No, over alpha, which gives plus square root of alpha y plus b over square root of alpha, all of it squared. And then because I added things, I need to subtract them, right? So minus b squared over alpha. And just for convenience, okay, I'm going to just go ahead and send everything to the other side and say, well, you know what? This is equal to a squared plus b squared over alpha minus gamma. Okay. Now, let me complete here. This is a squared plus b squared over alpha minus gamma. Interesting. So let's identify what's going on. So here, these are going to give me the coordinates of the center, and this here is basically telling me what the radius is, right? But for this to make sense, actually, let me factor this out. Probably that will look easier on the eye. Right? So I factor out the square root of alpha. I need to multiply here by another square root of alpha. So I get an alpha here multiplying that can go dividing to the other side. So this is going to be a squared plus b squared minus alpha gamma divided by alpha squared. Okay. All right. Let's check that I didn't mess up. So this gets squared. All right, we get alpha here. So we have this alpha that goes dividing, alpha squared. Everything looking good. Yes. But now, this only makes sense if a squared plus b squared minus alpha gamma is bigger than 0. Okay. If equals 0, it still makes sense, but it's just a point. Okay, so we find here this condition, and then we realize, oh, wait, what did we say before? We said that beta, where is beta? Beta. Here. Beta is a minus ib, right? So what we got here is magnitude of b squared. The modulus is a squared plus b squared needs to be bigger than alpha gamma, which is the condition we required. Okay, let's look at it one more time. So this condition here that looked a bit mysterious is just a condition that guarantees that we are looking at something that makes sense. Okay, notice that if alpha equals 0, this is 0, so this is going to be always true, as long as beta is not 0. Otherwise, it's silly, right? Because this would be 0, everything would be 0, everything is 0. Okay, so alpha 0, okay, satisfied. Now, if alpha is not 0, you need to require this so that you actually have a circle. Otherwise, it's either a point or it doesn't make sense, as we just saw. Okay, so now that we have the equation of a circle here, we can go back to the result we want to prove and prove that a Mobius transformation preserves this family of circles. So proof of part 1 of the proposition. Remember, there was a second part. We'll do that one in another video. Here we are going to use a typical trick that we use for Mobius transforms. Remember, we found in last class that Mobius transforms, the set of Mobius transforms is a group, and it is generated by just a few transformations. So it's enough to check the result for the generators. Of the set of Mobius transforms, okay, the group of Mobius transforms, because if ST both are Mobius transforms, then the composition Mobius transforms, and they both preserve circles in C, so does the composition. Okay, so this is the typical trick. You want to check a property for Mobius transforms, just check it for the generators of the group. Remember, the generators are what? Are translations, dilations, well, dilations or rotations. Okay, these two come together, or inversion / reflection. Okay, so translations, Z gets mapped to, well, let's write it with W. W equals Z plus B, be a complex number. Dilations, W equals AZ, A complex number. And inversion / reflection is W equal 1 over Z. Okay, so let's do the first one. Translations. Here we have W equals Z plus B, or Z equals W minus B. Okay, so if Z is in a circle, meaning it satisfies alpha ZZ bar plus beta Z plus beta bar Z bar plus gamma equals 0, and here as before, alpha gamma are, what happened there, are real numbers. How was this? Beta is a complex number, and we have the condition alpha gamma less than beta squared. What can we say about W? Okay, but this is very easy because once we know Z verifies this, and we also know that we can write Z in terms of W, we just plug in and see what happens. So this is alpha W minus B, W minus B bar, plus beta W minus B, plus beta bar W minus B bar, plus gamma equals 0. Okay, and here, well, you can do all the details, right? Because we have here the conjugates distribute, and then we can just do all the products. Here, what is going to happen, we are going to find alpha WW bar, right? Plus, and then here we are going to have W beta bar, B W bar, right? So we are going to get plus a beta minus, but then we have here also terms with those W's, right? So I'll just write the final result, and you can pause the video and do the algebra yourself. So beta minus alpha B bar W plus beta minus alpha B bar, all of it conjugate, W bar plus, and here we have an extra term, gamma plus alpha magnitude modulus of beta square. This is not going to fit in one line, so let's move to the next line. Alpha modulus of b squared plus gamma minus twice the real part of beta b. Okay, and all of this equal 0. And then we notice, okay, this has the form we intended. Okay, looks like alpha ww bar plus beta tilde w plus beta tilde bar w bar plus gamma tilde equals 0. Okay, alpha, gamma tilde are both real numbers for sure. Notice here, this is gamma tilde. So it's real, real, real. So everything good. What else? Yeah, beta tilde. Definitely this is a complex number, all right? Sorry. We need to check. Right, that alpha gamma tilde is less than the magnitude of beta tilde square, the modulus square. Okay, but this should be fairly straightforward because we have alpha gamma tilde. This is alpha gamma plus alpha square b square. I'm just taking the definition here, all right? Minus 2 alpha real part of beta b, right? Less than beta tilde square, which is beta minus alpha beta bar square, right? This we want to check. So let's see what we get. But this is equal to what? Is the magnitude of b squared, the modulus, plus alpha modulus of b squared. And then here, once you do the computation, you will find that you get minus 2 alpha real part of beta b. Okay. And that's it. That's all we need. Because now we just notice and say, hey, this term here, we got it here. This term here, we got it here. Okay, so there is cancellation. This is equivalent to alpha gamma less than modulus of beta square, which we know is true. So everything checks out. Okay, remember, there are two parts to this type of proof. First thing, we need to see that the transform W satisfies an equation of the correct type. Okay, alpha W bar plus number W plus conjugate of the number W bar plus another real number. And then we need to check that the coefficients satisfy the appropriate relation. Okay, and we need to check that by hand, just referring to what we already found. Let's look at the other two properties. The other two properties are easier, actually. Let's look at dilations / rotations. Okay, here W equals AZ, right? Or we could write Z equals, whoops, W over A. So here, what do we have? Here we have alpha W bar over A bar plus beta over A W plus beta bar over A bar W bar plus gamma equals 0. We're just plugging in the formula for Z. You see Z bar, beta Z, beta bar, Z bar. Okay. And now let's simplify. Yeah, that's it. So this is alpha divided by the modulus of A squared W bar plus beta AW plus beta bar over A bar W bar plus gamma equals 0. Everything checks out. So this is our alpha tilde, this is beta tilde, and this is beta tilde bar. Okay, I was being a bit lazy there, but let me not be lazy and just write the whole thing. There we go. And now we need to check. Okay, we need to check that alpha tilde gamma is less than the magnitude of beta squared. But look, this is the modulus of beta squared divided by the modulus of a squared by definition. And this is equal to what? This is equal to alpha over the modulus of a squared gamma. So everything looks good because we have alpha gamma less than beta squared, which is true. Okay, and finally, we can do the inversions. Slash reflections. Okay, this is W equals 1 over Z. This one is the easiest. So Z equals 1 over W, and we have alpha divided by W bar plus beta divided by W plus beta bar divided by W bar plus gamma equals 0. Okay, we are just plugging here the ZZ bar and so on. But now if we multiply everything by W bar, we get what we want. Only things are slightly misplaced, but all looks good. So we get alpha plus beta W bar plus B bar W plus gamma W bar equals 0. Okay, so everything looks good, except we have changed the roles of alpha and gamma. Okay, but that doesn't matter because you see the condition says alpha gamma less than modulus of beta squared. But when we change the roles of alpha and gamma, this condition doesn't change. So we are good. This proves that all three generators of the group of Mobius transformations send circles in the Riemann sphere to circles in the Riemann sphere, and we are done.